In this lecture, we are going to answer one of the very interesting question, whether when you are given a differential equation, the first question whether you can solve it, and if you can solve it, whether there are more than one solution. So those two questions are very interesting. So let's talk about the idea. So we're gonna talk about two questions, what we call the existence and uniqueness. Existence and then the uniqueness. So there are two questions for the existence, and if you know that the solution exists, then there's another question whether there are more than one solution. So let's consider this differential equation. So consider the differential equation y prime equal f x y along with y x naught equal y naught. So you have a differential equation and an initial condition. So then we have these two questions. The first question is, does a solution exist? So that's the first question. Does a solution exist? That's the first question. And so this is what we call existence. And then if there is a solution, then we go to the second question. What's the second question? Is the solution unique? Is the solution unique? So these two questions are also important. Like for example, let's say you are given a differential equation, and let's say you don't know that whether there's a solution, and then what can happen, what can go wrong is maybe you try to solve it using either numerical techniques or other techniques, and then but you know that without knowing that there is no solution. So that can be like a waste of time. So it is always a good idea to see whether there is a solution beforehand. Then you know that there is a solution, so you try to find it. And then there's another question. What's the other question? Is uniqueness. Why the uniqueness is important? You can see that, like let's say later we're going to talk about what we call the numerical solutions. So let's say you try to use a numerical solution because there are a lot of differential equations that you cannot solve. So then in that case, what you need to do is you need to find a numerical technique or the approximation. So when you try to go for approximation, the question is, if you don't know that there's only one solution, the question is which one you are going to find. So that's the problem. You try to find a solution, but which one? So that means, so in that case, the uniqueness is also important, because if you know that there's only a unique solution, then you guarantee that under the numerical technique you actually find that solution. So that's why the uniqueness is important. So let's try to get the idea. Let's try to solve this problem. So let's say solve let's say y prime equal 1 over x along with y0 equals 0, and you can see that it looks very innocent. You have y prime equal 1 over x, and then there's the initial condition y0 equals 0. So let's try to do the technique. So you can see this is like a very simple looking problem. So what we normally do in this case, we can integrate. So right, so we can integrate. So integrate to find dy over dx equal 1 over x. So this is dy over dx 1 over x, and then when you integrate, so what we normally do is this is like a, you can separate the two variable. So you're gonna get dy equal 1 over x dx. So this is a very simple. You can integrate both sides. Once you integrate both sides, you're gonna get y equal ln x plus c. So everything looks good so far, but now the problem is when you try to find the condition, the unknown c, you see that you're gonna get stuck, because the unknown, the y, to find the unknown, you cannot plug in 0 in there, because we know that log 0 is not defined. So if you look at the log graph, so this is the graph of logarithm. So it's like a tunnel. So that is the graph of logarithmic function on the two sides, because the absolute value, that means you have two sides. So you know that at 0 the function function does not exist. So how to find it? So there's no way you can find. So because of that, you can see that this does not satisfy this. Does not. This does not satisfy the initial condition. The initial condition. This does not satisfy the initial condition. So the initial value problem does not have a solution. So the initial value problem. What's the initial value problem means? The differential equation and the initial condition. When you combine both, we call it is the initial value problem. So in this case, the initial value problem does not have a solution. So the initial value problem does not have a solution. So you can see that a very innocent looking problem may not have a solution. So in this case, you can solve the differential equation part, but once you try to find the constant, there's no way you can find a constant that satisfies the initial condition. So that means there is a problem now. And also we can see that in a different way. So let's look at the directional field for this problem. So you can see, so the directional field looks like this. So so we have y prime equal 1 over x. So the directional field looks like 1 over x. So that means when you have a smaller value, so it is steeper. So it's like that for smaller value, and the value is getting larger, it's going to be less steeper. And then and it's much more less. And then the same thing, but change the sign. So that means if you go to the other side, it's going to look like so it is more steeper on this side, like that, and then less steeper, like this, and then even less. So that's the kind of shape of the directional derivative, because it does not depend on the y. So that's why they like kind of parallel. Okay, that's the directional field for this differential equation. So that is the x, and then this is the y. And you can see that this is just 1 on y equals 0, the y. And you can see that you cannot draw directional field for x equals 0. Now the problem is, and you can see that if you try to draw a typical solutions, so how the typical solution looks like. So you can see that it just follow the directions. So that means typical solution looks like this. So if you start here, it's gonna follow the line, so it's gonna go like that, and here it's gonna go like this. So that's how the typical solution looks like on this side. And on the same thing, if you look at the other side, so this is how the typical solution looks like. So, and then because it's gonna follow the line. So now you can see that. So the problem is, there is no way you can pass from one side to the other side, and also there is no solution that passes through this point, because there is no directional fields that pass through this point. Okay, so you can say okay, so there is no directional fields, directional field curve that passes through So you can see that none of them passes through that point, so that means there is no way you can find a solution that goes through that point. So that's the issue here. That's the issue here. So now the question is how you can actually find this. So there is a like nice theorem called the Picard's existence theorem, and that's gonna give you a criteria to check whether there's a solution or not. So let's talk about that. So this is a theorem, so we are not gonna prove this, we just give the theorem. This is called the Picard's existence and uniqueness theorem. Existence and uniqueness theorem. Picard's existence and uniqueness theorem. So what the theorem says, so what we're gonna do, we are gonna look at this problem. So what problem? So we can look at the general problem, y prime equal fxy along with y x0 equal y0. So that's the problem we are looking at. So that's the general problem we are going to look at. So for this problem, what the theorem says, so theorem says that if fxy is continuous, so there are two variables in both variables, continuous, and the partial derivative with respect to y and the partial derivative of f with respect to y variable exist and continuous, near some point x0 y0. So that's the x0 y0 point that you are talking about. Near some point x0 y0, then a solution to y prime equal fxy along with y x0 equal y0 exists and is unique. In an interval containing x0 y0. So what it says that so if the function fxy is continuous, one condition, and the partial derivative with respect to the y variable is a dependent variable, is the partial derivative with respect to y variable exists and continuous near some point x0 y0. Okay, so there's a point x0 y0 near some point x0 y0. Then what it says that then there is a solution, then there's a unique solution. So it says that there is only one solution in some interval containing that point. So that means you can find an interval that on this interval, at least on this interval, it exists. That's why it says that at least, because we don't know what's going to happen outside, but it says that on this interval, wherever the function continuous and wherever the partial derivative exists and continuous, on that same interval there is a solution. That's what the Picard existence theorem says. Okay, so yeah, on that interval, this interval may be large, maybe whole set of real numbers, but we don't know that yet. Okay, so it depends on whether those two conditions are satisfied. So let's look at maybe two examples and see how we can kind of apply this idea. So let's look at the first problem, then we can see what actually went wrong with that. So so let's have a note for that. So let's say so let's look at the first example. In the initial value problem, y prime equal 1 over x, y0 equal 0. The function, you can see the function fxy equal 1 over x in this case, that's the function of xy, is not continuous, in the domain, at least near x0, near 0 0. So that's the problem. Okay, so because of that, so it does not it's not continuous. Because of that, there's no solution. Okay, according to Picard's theorem. So by the Picard's theorem, there is no solution. There's no solution. So that's what happened. Okay, and also let's look at another problem. So let's see this one. So the next example, solve. Let's say y prime equal to absolute value square root along with y0 equals 0. Now what's the problem here? So you can see that in that case the function is continuous. Okay, so here fxy, which is 2 absolute value square root x, is continuous on the whole set of real numbers. What is the graph of this one actually? So if you look at the graph of this function, so it is the square root function but on both sides. So that means it's going to be like that on this side, it's going to be like this on that side. So that is the 2 absolute value. So that is the 2 square root absolute function. That's how it looks like. So you can see that this is a nice continuous function. But what's going to happen to the derivative? So let's look at the derivative of this function. But the f with the partial with respect to y. So what is the partial with respect to y of this function? And you can see that so it is, if you take the, so it is 2 times 1/2 1 over again absolute value square root. That's what you get. So that means if you simplify this one, it is a 1 over so you can see that square root y. But again, so you have to be careful with this because if you go to the negative side, it's going to be negative. So there's a sign issue here. So actually what we normally do is the best way to do this is you have to consider two different sides for this one. So you have to consider the positive y and the negative y. So that means depending on the positive or negative, actually you're gonna get, so I'm gonna write this one. So it's maybe like slightly different what we get. So you're gonna get a, so you have to consider 2 signs separately for this situation. You can just write a general one. So what's gonna happen is it is the sine of y times 1 over square root y. So that's what you get. That's a sine y, because you can see that if it is on the negative side, so it's going to be negative. So but that's still, so that's still, you can see if you look at the absolute value, just absolute sign, absolute value, you can see it is 1 over square root y, but it's on the negative side, it's a negative slope. So that means so what's going to happen on this side, it is a positive slope, on this side is a negative slope. So because of that you need the sine term here. Okay, so that's what happened. Now what's going to happen, and you can see that this does not. So you can see this does not exist. This does not exist at 0, 0. So that's the problem. That means it's violate the second condition. Thus violates the second condition. So that's what happened. So let's do one last example. So how about this one? So let's say actually before that I would like to say like what exactly gonna happen here, and so let's try to kind of see what's gonna happen here. So you can see that so something is wrong, because you can see so this violates the second condition. So what's going on here? So it's when the first condition is not satisfied, you could not find a solution. But now what happened? Actually this create a issue to the uniqueness. So now you can see that if you try to integrate this one, so what's gonna happen? So you can still integrate this one. So if you integrate this one, what's gonna happen now? So you can see that first you can see note that y equals 0 is a solution. Okay. Note that y equals 0 is a solution. So there's a y equals 0 solution. But the question, so the question is whether are there any other solution? Okay. Are there any other solution? Are there any other solution? So you can see that yes, there is another solution. So that means it's going to violate the uniqueness. So let's see what's the other solution. So you can see that for positive, let's integrate this one. So we can integrate for positive values. So for y positive, what we can do, we can write this one as y prime equal to square root y, and then you can write this one as dy over square root y equal to dx. So and then we can integrate the two sides. Once you integrate the two sides, what are you gonna get? So this is y. So what's the easiest way to integrate this one? You can write this one as y to the negative 1/2 dy equal to dx, and then what will happen? You can add 1 and divide it by that. So when you add 1, you're gonna get y 1/2. When you divide by 1/2 means multiply by 2. So you're gonna get here 2x plus c, like that. Now what you can do is actually you can square both sides. So so this simply gonna give you that 2 square root y equal 2x plus c. If you divide by two sides, if you divide by 2 both sides, so you're gonna get a solution as, so your solution becomes, I'm gonna write the solution here, y equal x. So let's write it. So what I'm gonna do, I'm gonna write this one as yeah. So let's write it like that. So I'm gonna divide by 2, and then we can write this one as x have 2. First you divide by 2 and then you square it, so you get like that. Now using y0 equals 0, if you plug in y0 equals 0, what's gonna happen? You're gonna see that c equals 0. So that means your solution gonna be y equal x squared. This is for y positive. Now for y negative, actually not the y positive, okay. So let's see what is the consequence of this one. So we know that the y negative. Okay. But the partial derivative with respect to y, fy, which is we're gonna consider this as positive and y negative, two cases. So if you consider the positive case, you're gonna get 2 times 1/2 1 over square root y. And then what's going to happen, if you consider negative 1, you're going to get a negative sign. So that means what we normally do is we're going to say sine of y. So that means finally you're going to get sine